And I am turning it over to Dr. Hung Tao Shi, who will be introducing Bradley Stobba.
Hi, everybody. Yeah, my name is Hung Tao Shi. I'm one of the physics professors here in the department. I came to know Brad about 2 years ago when he transferred to SSU. Last fall, he came to me, he asked me if he could do a hands-on project. Back then, I wasn't really sure because of the pandemic, but we decided to give it a try. So in the fall semester, he did a lot of readings, getting into all the literature, the books, and so this spring semester, believe it or not, we were able to manage to do many things in the lab, and I was really impressed with his dedication, effort, and time management skills. So I hope he learned a few things in the lab and move on from here. Brad, the floor is yours.
Awesome, thank you for that introduction. Share my screen. Okay, so good afternoon, everybody. My name is Brad Stobba, and for my capstone project, I decided to fabricate Schottky diodes Schottky diodes made of zinc oxide and gold. Once we had these diodes fabricated, we measured a current at a particular voltage and then created these current versus voltage curves. So the reason I chose this project is because I wanted to gain some hands-on experience with semiconductors and also get familiar with some of the lab equipment in the Keck lab. So for those of you that don't know, semiconductors play a huge role in our day-to-day lives. They help create the electrical components that make up solar panels, cell phones, cars, and even computers. So research in this field has really helped, I guess, mold our society and created that technological based society that we see today. So for this presentation, I'm going to briefly talk about semiconducting materials, then touch on some Schottky diode basics, and then go into my research. So what is a semiconductor? A semiconductor is a material that has a conductivity in between that of a metal and an insulator. So I think the easiest way to visualize this is by looking at an energy band diagram, which we have here. And so it's broken into 3 separate bands. The lowest band is the valence band. And this band is at the lowest energy level, and the electrons are bound, so they're immobile. The band above that is the band gap, or the forbidden zone, and this is an area where electrons cannot exist. At the highest energy level, you have the conduction band, and this is an area where electrons are allowed to flow freely, where they're not bound. So in order for a current to flow in a semiconductor device, an electron has to absorb enough energy to jump from the valence band up into that conduction band, and then be able to flow. Something to note about semiconductor materials is that you can dope them, and so that either creates an N-type or P-type semiconductor. And so an N-type semiconductor has extra electrons, where a P-type semiconductor has extra holes. So the semiconductor we decided to use was zinc oxide. And so this has a wider band gap of around 3.3 electron volts compared to some other common semiconductors such as gallium arsenide or silicon. And another thing to note about zinc oxide is it has this hexagonal structure where silicon and gallium arsenide have a diamond structure. So that's a little bit about the semiconductor material. Now into the Schottky diode basics. As you can see here, a Schottky diode is the junction is formed when you have a junction or sandwich, a metal material and an N-type semiconductor. So at equilibrium, or if there's no applied voltage across this device, you have this depletion region that gets formed. So the atoms in the N-type semiconductor are ionized because electrons leave them going into the metal. These ions then induce a charge in that metal, creating this built-in potential or E field. And so this built-in potential is what's responsible for that exponential behavior we see in a current versus voltage curve for a Schottky diode. So when you apply a voltage across a Schottky diode, you can either have it so it's forward biased or reverse biased. In a forward biased diode, this depletion region or built-in potential and the applied voltage actually go against each other. So the applied voltage, if it is high enough, will overcome that built-in potential, completely reducing it and actually allowing current to flow through to the diode. Where for a reverse biased Schottky diode, you have that depletion region and the applied voltage going in the same direction. So it causes that depletion region to get bigger, increasing that resistance and effectively stopping the current from flowing through. So for this talk, we're going to focus on the forward biased Schottky diode. And so here is a current versus voltage curve. As you can see, voltage is on the horizontal axis and current is on the vertical axis. If you look at the positive quadrant here, you can see that the current has this exponential dependence on the applied voltage. So here's the equation up here where I is the current and V sub A is the applied voltage. So this blue curve is the Schottky diode, and this yellow curve is a rectifier diode, another common diode. As you can see, the Schottky diode has a lower built-in potential or turn-on voltage than a rectifier diode. And so this lends it to low power applications because you can have the same current at a lower voltage. Another thing to note is that Schottky diodes are good for fast switching applications because they are a unipolar device, whereas a rectifier diode is a bipolar device. So for the research process, it's kind of broken into 5 different sections. The first was the preparation of the substrate. The second was the electrochemical deposition process. Next was the laser-induced photoluminescence, and then the forming of the metal semiconductor junction, so the creation of that Schottky diode, and then collecting the current versus voltage data. So for the preparation of the substrate, we had this ITO on glass, and we cut it to the correct size for the deposition process. Once we had that correct size ITO, we spin-coated gold nanoparticles onto this ITO, and then thermally annealed those gold nanoparticles onto the ITO at 250 degrees Celsius for 30 minutes. This helped create a uniform seating layer for that zinc oxide. For the deposition process, we had the chemical solution inside this Teflon cell here, and the glass ITO is exposed to the solution and at the base of the cell. The ITO was negatively biased at 3 volts. As you can see, it's connected here, and then there was a platinum wire going into our chemical solution. The growth temperature was 80 degrees Celsius, and this was kept constant throughout the whole process. And the only thing that varied was how long the growth process ran for, so either 15 minutes, 30 minutes, or 45 minutes. We monitored this using a LabVIEW program. And then up here in the upper right-hand corner, you can see what a finished sample looked like. So this is our zinc oxide on our glass ITO. So after we had that sample, we moved on into the Keck lab and used a scanning electron microscope to gather some images. So for our 45-minute sample, you can see that the nanowires are much less uniform than our 15-minute sample over here. So the 45-minute sample has a lot of the nanowires laying down in plane, where the 15-minute sample has a lot more nanowires normal to the surface plane. For our 30-minute sample, here I did a little close-up so you can see that hexagonal structure of the zinc oxide, so kind of a stop sign shape. And from here on out in our talk, we're just going to focus on only the 30-minute sample. So we took that 30-minute sample and cut it in half. With one of the halves, we thermally annealed it again at 300 degrees Celsius for 30 minutes. And this thermal annealing process is just to try and help heal the crystal or remove some of those imperfections. So once we did that annealing process, we used a nitrogen laser that had a wavelength of around 340 nanometers. And we shined that laser onto our sample. So some of that light or that energy from the laser was absorbed by the zinc oxide, and that excites an electron from that valence band up into the conduction band. When that electron falls back down from the conduction band into the valence band, it emits a photon of light. So our sensor here captures that photon of light as well as the reflected light from our nitrogen laser. So this one on the left was for our annealed or our unannealed sample, and the one on the right is for our annealed sample. The first peak on both of these graphs is that reflected light. So it's around 340 nanometers. And the second peak is from our emitted photon, and that's around 384 nanometers. So from this 384 nanometers, we can calculate the energy or the band gap of our semiconductor, which is, we ended up with 3.23 electron volts, which is pretty close to the predicted 3.3 or expected 3.3 electron volts. Another thing to note here is that the annealed sample had about 10 times the light emission of the unannealed sample. And so that came from our integrated time being, four times less, and also our intensity peak being almost twice as high. So from here, we decided to just focus on the annealed 30-minute sample for our IV curves. In order to get those IV curves, we had to form a metal semiconductor junction first. So we used our DC sputtering device in the Keck lab and sputtered gold onto our zinc oxide material. And so we created these separate contacts using a mask. And here in the upper right-hand corner is that gold on the zinc oxide. Once we had those contacts, we cut a small piece of indium wire and put that on top of the contact. And this was just to help protect the crystal during our measuring process. So here's an IV curve for our annealed zinc oxide sample. So the first run is in yellow. And as you can see here, it has that nonlinear or exponential growth. But we kind of have this step sort of function happening here. And also there's this negative differential resistance occurring right here. And so this negative differential resistance is where that voltage is increased, but you get a drop in your current. And so we saw this usually on the first run, but then you can see for the second and third run, this ended up smoothing out. And so we were kind of wondering, is this, Dr. Hung-Tao Shi had seen this negative differential resistance before, and we thought, oh, will annealing the zinc oxide remove this? And it turns out it didn't. So we thought, okay, let's try and anneal the zinc oxide sample with the gold contacts on there and see if we can remove that first run negative resistance. And so we did that. We annealed it with the gold contacts on there, and here was our runs. This time the first run is in blue, and as you can see, it is very crazy all over the place. And then our second and third runs started to smooth out and show that exponential relationship that we should see. So the conclusion was that annealing did not remove that negative differential resistance. From both of those curves, both of those IV curves, I took the smoothest sample and then mapped out the built-in potential using these lines here. And you can see they're very close to each other. And the blue one, which is the one that was annealed after the gold contacts were put on, actually has just a little bit smaller of a built-in potential than the one that was only annealed as a semiconductor, so before the contacts. And this was a little bit unexpected. So in conclusion, we saw that expected exponential relationship between the current and applied voltage. Also, that built-in potential barrier was very similar when the sample was annealed before and after the formation of the gold contacts. And that negative differential resistance is potentially due to the initial surface states of the zinc oxide, but more research has to be done to kind of determine this. But we were only seeing it on the first one or two runs, usually with each sample. And so I'd like to just give a quick thank you to Dr. Hung-Tao Shi for all of his guidance and help with this research process. Also Ryan Brown for all your help this semester in the lab. And a huge thank you to all of the physics and astronomy faculty for making my time at SSU fun and full of learning. And then a thank you to all my friends and family for their continued support through my physics journey. So I am open for questions.
Let's do applause, looking for the emoticons. So Bradley, you see all of that. Fantastic. Let's look for a hand raised in amongst the hand clappings. Does someone have a question for Brad? If not, oh, okay, here we go. Alex, please.
Great talk. So I was wondering, so you had this issue with the first run, right, that you were trying to get rid of. But so if you were building this device to actually be used, you know, among some other circuits or something, would it be all right, the fact that you can, you know, is it sort of just that you can use it once and then somehow it evens out and then now it's a good working device? Or
Yeah.
am I understanding that correctly?
Yeah, I guess so. That was kind of the thing, is if we let it sit for a little bit and then came back and ran it again, you know, say for the first time, you would still see that first initial run would be a little, you could see that negative differential resistance. And so I guess for it being useful in a circuit, you'd probably need to like do that, have that reoccur consistently for, I think, each run, not over, you know, a very extended period of time.
Right, I see. So definitely not ideal.
Yeah, not ideal.
Great, thank you.
Good. Well, I'm scanning for other questions. We'll give another moment if someone has a question. Do feel free to throw your hand up at any point. But with that, let's thank Brad again. A very good job. Thank you so much.